And now I'd like to introduce you David Mytton from Server Density, and he will present Puppet at the center of everything. Please.
Good morning, everyone. So my name is David Mytton. I'm the founder of Server Density. We do server monitoring and website monitoring and help you provision your infrastructure. So you look at your websites from different locations around the world, how fast they are, whether they're up, and then we get into your servers so we can give you graphs and alerting and help you fix those problems. The company's been around for about 4.5 years now. I started it back in the beginning of 2009, and we're now deployed on around 100 servers, all of which are on Linux on Ubuntu 12.04 on the LTS release. And we have about a 50-50 split between virtual instances and dedicated hardware. And we're deployed across 2 primary data centers with SoftLayer in the US, but we have 20 or so countries that we monitor websites from. So we have a large number of nodes around the world, but our primary deployments are in the US. And the platform, the product, was originally PHP and MySQL, but over time has migrated to pretty much 95% Python now, with MongoDB as the data store, and we use Nginx as our load balancing. And we're processing about 25 terabytes of data a month through the system. So it's fairly high performance. It's at the largest size of things, although it's not massive when you look at some of the bigger deployments that are around. Now, the focus of this talk is going to be about our use cases for Puppet. And like everyone else, we're using it for config management to help us control all of our servers, make sure they're standardized and that everything is deployed consistently. But what I'm going to spend most of the time on is some of our more unusual use cases, which is how we can use Puppet to manage failover within a single data center between nodes in load balancing platform, but also across multiple data centers and how we can use Puppet to failover between them. And we also use Puppet to deploy our application, and I'm going to talk a little bit about how we do that, so that any of our developers, anytime, can press a button and have builds deployed to staging or production, and how we use Puppet to do that. And also some more general sysadmin tasks and how we use Puppet to deploy system updates and application updates in terms of things like databases and web servers across all of these 100 nodes around the world. So just to begin with, I'm going to spend a minute or two just describing how our configuration works. And this was set up about 2 years ago. And for the first 2 years of the company, we had no config management, purely because we were growing very quickly. We had a relatively small number of nodes, and we didn't have time, didn't really understand how to use the config management tools back in those times. We switched from an old hosting provider to SoftLayer about 2 years ago, and at that point decided it would be a good idea and good opportunity to properly define our entire infrastructure so that we could move things over and have them ready into Puppet and defined just to make the migration easier. And we started off by creating a base manifest. The Puppet Forge has only recently become really good, and so we didn't really use any of the publicly available modules. We simply described our setup using a base manifest that was divided into different classes so we could categorize our nodes. This was because it was very, very quick to set up. Nowadays, we use modules from the Forge when we're deploying new applications. So we recently started using Nginx about a year ago and took the Forge module, expanded on it, and uploaded it back into the community to add some extra things, particularly around SSL and load balancing, some of the things that we needed on there. But this has significantly sped up how we can deploy things and made everything a lot more modular. And all of our Puppet manifests sit in GitHub in a repository, a single central repository that we use that is updated on the Puppet master every 10 minutes. And this is very, very straightforward, very simple. It's a nice way to get access to the code to everyone. You've got an audit trail because it's in Git. And we can use pull requests to do code reviews. So changes are made in branches, they're reviewed by the team, and then they're merged in so that we always have a control we can roll back if necessary. And all these custom manifests were based on moving those instances from our old hosting provider over to where we are now. And we have a base module which applies to every single one of these servers. And this defines standard system packages, stuff that's consistent across every single one of the nodes, things like time zone support, and Python versions, Git versions, the stuff that we want to have on every single server. And we conceptually think about how our infrastructure works in a hierarchy. And this doesn't actually exist per se within Puppet itself, but it's a good way for us to think about how all these nodes relate to each other. And we have that single base node, which sits at the top. And then we have conceptually separate levels of hierarchy that we put each of the different nodes in. So for example, we have a soft layer node, soft layer manifest in class, so that specific rules that need to be applied to servers that are just on soft layer just appear and get assigned to this group. And then the base module gets applied on top of that. So the way that we think of it is by having these different levels. So we can apply rules to specific hosting providers, different applications that we deploy, and we can group these conceptually within our infrastructure. So there is a hierarchy as far as we're concerned, but in Puppet itself, they're just all on the same level. But this gives us a good way to think about how our infrastructure is set up. Now moving on to the failover situation, and this is where it becomes a little more interesting and a little different from what a lot of people do. And the main way that we do this is by having our own custom DNS within the entire application. But we don't implement this yet using an actual DNS system. We don't have bind or anything running internally. We simply define an essentially hard-coded host file. It's hard-coded in the sense that the hosts are in there, but it's defined completely by Puppet. Our entire application is split up into different components. It's a service-oriented architecture. So each part of the system has its own load balancers, its own web servers, its own databases, and these are all exposed internally over an HTTP API. So when different parts are communicating and interacting with each other, they're doing so using internal host names. And you can see here we've got alerting system, we've got audit, authentication, data store, and various different parts. And these are all defined using a variable within Puppet. And this then gets written in when the Puppet manifests run, when it gets compiled, and it allows us to specify where all these endpoints are consistently across the entire infrastructure. But we do this by defining it within the Puppet Enterprise management interface, because this gives us a very easy way to make changes, particularly in failover situations. So if you consider something's gone wrong in the middle of the night, you want to have a very easy path to making changes, whether that's moving servers out of a load balancer pool or failing over to a different data center. You want to make this process as simple as possible. And having a command line way of doing this introduces potential errors, particularly if you're tired, you're not sure what's going on. So to allow us to have our entire ops team easy access to the entire infrastructure without necessarily having to log into SSH immediately, for simple failover cases, we can handle everything through the Puppet console. This is because we're defining those IP addresses on a global level. So at the very top, we've got a number of hosts that are defined, and these are the variables that then get replaced into the host file. And it's very easy within the Puppet interface to change these. It's simply editing the field, saving it. And then we can apply these changes across different nodes selectively. So we can force the Puppet agent to run. Once we've made a change, we don't have to wait for its normal update cycle. But we can also apply these selectively to specific nodes. So in some cases, we're deploying changes selectively. So we can deploy them to a group of servers and monitor them. So if this isn't a failover situation, but we want to deploy some new code just to a specific load balancer pool, we could do that. And you're effectively A/B testing internally, because we can choose the specific nodes that are being applied to. And the reason we're using the graphical interface to do this, because you could easily do it on the command line, is just to make it simpler. And it allows us to restrict access to the production environment so that engineers can make changes to things without necessarily having to involve the operations team or to log into servers directly. And it just makes it significantly simpler. And this is how we handle our load balancer pools as well. Within the Nginx manifest, we've made changes to allow us to define what the nodes are, so when they're proxying requests through to the web servers behind the load balancer front end, these nodes are defined within the Puppet manifest. And it's simply a comma-separated list, which we then extract out within the Nginx module itself. So it allows us to very easily control the load balancer pool without having to, again, use the command line. Well, previously, we used the pound load balancer, which is a software load balancer for Linux. It's fairly straightforward and simple, but the command line tool for it is not that easy to use, particularly when you want to make configuration changes to the load balancer pool. Everything is referenced in various levels of hierarchy with numerical references, which can be confusing. By abstracting this out and putting it into the Puppet interface, again, it makes it very easy to do these changes. It's just a list of our hosts, and anyone can make those changes. So when we are in a failover situation, we can have it as part of our normal to-do list, the checklist that you should have when you're going through different failover situations. One of those points can simply be remove the node from the list, and you don't have to know any special commands to do that. You don't have to look at any manual pages. You can simply remove this from the manifest. And this is how it looks in the Nginx manifest itself. We're defining those different front ends and simply doing a replacement by pulling out the commas and creating the array that then gets put into when Nginx is building its config files. And we also use a similar method when failing over Puppet itself. Because we run Puppet as a single master, there's a single point of failure there. But we have a secondary Puppet in a completely different data center that's ready to take over. But the problem is that handling that failover automatically is fairly complicated. And the way we do this is by defining the Puppet host with a public IP address. But this isn't just any standard IP address. This is a feature from SoftLayer called their global IP. And this is very similar to an Amazon Elastic IP address, in that it can be pointed to any one of our nodes at any time. But unlike Amazon's Elastic IPs, which are restricted to a specific region, the SoftLayer global IP can be pointed to any single node anywhere in the world, and it will update pretty much instantaneously. And this, again, is done using their control panel. You can log in. But we have scripted a number of instances where we can detect failure automatically, and using their API, we can make changes. So if we need to fail over to a different data center or the Puppet master is down, then we simply repoint this IP address to the new node, and all the routing happens internally within SoftLayer's network. You could use the same thing with the Amazon Elastic IP address, although you would be limited to a specific region. So you could do this on a DNS level instead. And OpenStack has a similar feature with their floating IP addresses. Now, the thing with outages is that you have to expect they're going to happen. It's impossible to get 100% uptime, and although you can do things around high availability and building out your infrastructure to get as many of those 9s as possible in your SLA, it's going to be impossible to get to that mythical 100%. Even the likes of Google can't do it. So you have to expect that you're going to have failures and figure out how you're going to deal with those. And Puppet really helps you to do this. And it helps by allowing you to test all your different applications. You can move nodes around, you can change things, you can simulate failures. But one thing you should also be doing is testing the vendors, not just on the software packages that you've got installed, but also on their support. And there have been a number of cases where the support that we've had contracts for from different vendors has not come through when we've needed it. And one example was that the phone number in the UK just wasn't routing to the US when we needed to phone it, and had to phone their US number instead. So making sure that when you're testing things, you're actually testing the support you've got. So if you've got a 24/7 support contract, you can actually get support. And this is part of your just normal testing cycle. And where Puppet comes in is when you're simulating things, because in a failover situation in the real world, there's going to be a lot of confusion. You will need to make sure you've got everything documented. And the only way you can actually test this is by simulating either a real outage by treating some kind of problem during working hours, or more likely simulating that by taking nodes out or having some kind of war games. And this isn't something that we do to that level of extreme that we want to at the moment, but there are good examples from companies. Google is a good one about how they simulate these things so that their operations team actually thinks there's an outage, and it allows you to monitor and to test and see what's going on without actually having an outage that is affecting customers. So you can go through your documentation, you can make sure everything's there, it's up to date. People have got the right checklists, they know where to go, people have enough knowledge of the system to be able to fix these problems and how they can work with the tools, whether that's Puppet helping you with failover or the command line tools. The way Puppet comes in is by allowing you to control your infrastructure from a single location. So you can execute commands across many servers to simulate a particular failure. And instrumenting Puppet to do this is a good way to have a central control when you're actually running that simulation. Now, the next use case that I'm going to talk about is how we do code deploys with Puppet. And this is a process that we go through. There's a standard process that everyone goes through to deploy code, and it always starts with the commit. And this is where engineers are committing code into our GitHub repositories for the different applications. And as I mentioned with our Puppet module, Puppet repository, we use a branch model so that every developer is working on a branch, either related to a specific bug or a feature that they're working on. And these changes are pulled down and worked on completely independently from the master branch, which is what we always consider stable and is almost always out on production. There might be an occasional time where we're deploying a particular branch to production just to test it, but generally speaking, master is always considered stable. All of this is also replicated locally. So all of our engineers have a Vagrant instance or multiple Vagrant instances which replicate our entire environment. And because we use Puppet to manage everything in production, we can use those exact same manifests in Vagrant to simulate a real production environment on every single developer's machine. And this gives us consistency, because the worst thing you can be doing is developing in an environment that's different from your production environment. And by using Puppet that builds the Vagrant instance, it installs all of the components, it sets it all up as if it was in production, just on a single VM, rather than deployed across 100 nodes. And this means that developers can work with particular branches of different components, but they always have the latest version, and it's all consistent with production, minus the actual production data. And once a commit goes out to GitHub, we trigger a build, and this is done using BuildBot, which is an open source tool. It's similar to Jenkins. We originally moved from Atlassian Bamboo to BuildBot fairly recently. And this runs our entire test suite. So every part of all of our components has testing to as much as we can. We're always trying to build those up, as everyone is. But it runs unit tests, code syntax testing, and probably more importantly, integration testing, so that we can validate our internal APIs, we can make sure things are working for our customers. This happens on the master branch, but also every individual branch. And it builds immediately so that we get feedback. We know when things are broken, who's broken them. But it also builds our production packages. Now, we're deploying mostly Python, but also some PHP. And the front end has a lot of compilation in the JavaScript and the CSS side of things. So we have packaging that goes as part of that. And within Python, that's build out. PHP, it's composer. As part of the front end, there's various other build processes that happen there. But this build process also builds those packages. And one of the advantages of something like build out or composer is that it creates a completely isolated environment for your code to run. So we define all of the dependencies, all the Python packages, for example. They then get checked out in an isolated environment to the specific versions that we require. And this separates it from the system deploys, the system versions of those packages. And it means we have an isolated environment on each server that gets deployed. But it does have a build step. They've got to be checked out. Various things have got to be compiled. And this happens at the same time. So the build not only runs unit tests and all the tests around that, but also creates the packages that we then deploy out to production. And these are essentially the build artifacts. It's the result of the build that then gets deployed to production. And it's the deploy process that is where Puppet comes in. And this is done by looking at the version that is deployed on each of the web servers, each of the application servers behind each component. And we do this by defining a build version that is available internally just as a simple file that's served via HTTP. And this build version is essentially the git commit. And when we click the build button, the build version on each file is changed, and so when the Puppet agent runs, it notices the difference and copies the packages over. Now we've built a user interface on top of this so that our engineers can see what version is deployed on each of the servers within our environment, and we can see when it's green, which means it matches master, and when it's red, it means it's out of date. And any of our engineers can log into this interface at any time. They can see all of the branches, all of the builds, and they can choose which nodes they want to deploy it on. And we call this Panda Control because it replaced Atlassian Bamboo and Pandas Eat Bamboo. So any engineers can go in and choose any of these nodes, whether it's production or our staging environment, and deploy the code. When it's the staging environment, it's mostly the branches that are going out because we test locally on Vagrant. We then create a pull request and test it on staging, and then another engineer also tests it on staging, make sure everything is consistent before we deploy it to production. Once the engineers decided that they're going to deploy it, whether that's to staging or production, you tick the servers that you want, you press deploy the build, and a change happens on the nodes that you've been selected to adjust that build version file. And we then use mcollective to trigger a Puppet run on each of the selected nodes. And it's this Puppet run that actually deploys the code. And we use HipChat internally. Half the team is remote. We've got an office in London, but the company started remote for the first 3 years. So we're set up, and we have a centralized chat room. And you can use Campfire for this. GitHub use Campfire. We use HipChat just because we think it has more useful features, but it doesn't matter because they both got APIs that allow you to post messages into the room. And this, did you have a question? Yeah. Yeah. So the question is how we handle schema changes on the database. So we use MongoDB, so there is no schema. So yeah, we don't have to do anything. Yeah, we don't have to do anything. It's a valid point, though, because yeah, schema changes are a pain and are very complicated. So switch to MongoDB, or you would have to script this into the process. We don't have to do that, so I can only speculate on how you might do that. But yeah, that would be a difficult one. So the process gets posted into HipChat. So the build is completed here at the top. You can see the UI build has succeeded. The next step is that someone has clicked the deploy button. In this case, we've got a master button that allows us to deploy every master from every branch to staging, all in one go, rather than going through every one individually. You can see that's happened. And then a minute later, the first deploy has come in. And this is where the Puppet agent has run. It's noticed that the build version that we've written on the web server, in this case it's the staging 1 server, it's noticed that that build version is different from the version that we've decided is now the true version. And because there's that difference, it's going to trigger the deploy of the code. And the deploy, in the case of PHP, it's very simple. It's just writing the files over. But in some cases, we've got to restart things. So with Python, we use Celery for our queue processing. So when data comes in or when we've got to send out alerts, then we have a queue. And we've got to restart those queue daemons. So there's a script that runs that could be specific to each component. And as part of the Puppet run, it copies over the files, it does it in the correct order, and then triggers any restarts that need to happen. And we get live feedback within our HipChat room so that not only can the original developer see what's going on, but it gives us a feed of the entire company. Upgrades go in there, some new signups, code commits, build deploys, everything that happens within the company during the day. Everyone can see what's going on. And this gives you, if you're away for a couple of days, you could easily scroll through and see what's happened. Or if you're coding for a couple of hours, you could scroll through and you don't get notified or interrupted. But it means that everyone's always aware of what's going on, what code has been pushed out, and when that's happening. So It was about 6 months ago that we built this build system, and it replaced something similar but not quite as advanced. And the reason that we decided to use Puppet for this, there are a couple of reasons. The first is the APIs behind it. Puppet is the one true source that defines your entire infrastructure. There's no other source than the systems themselves, and because the systems are controlled by Puppet, it is a central repository. And we can then use that to query what's going on in the infrastructure as a single source. It's also already there. It's on every single one of our servers. We don't have to write our own custom daemons. We don't have to create our own file server. We don't have to deal with how to run commands across different servers. We're standardized across Ubuntu Linux, but if we were part of the way through upgrades on different systems or had different environments, Puppet gives you a single API, a single way of accessing all of this without having to build our own deployment system. And we get access to system facts. And this isn't something that we use extensively at the moment, but you can query Puppet to do things depending on what operating system you're on, what versions you're on, what file systems are available, and we do this when we're deploying between virtual instances and physical hardware because we have different disks set up and they present those in a different way to the operating system. But there are some disadvantages, and the main one is that it's slow. Now, it can take just a couple of seconds for the Puppet agent to run. And this is the case on our very high-spec servers, on our database servers, for example. But on our monitoring nodes that are in those 20 different countries, they're very, very low-spec VMs because they only have to do web requests, and it's very, very easy. It's very lightweight to do that. And on those, the Puppet agent can be quite slow to run. And by slow, I mean it's going to take more than 30 seconds to complete. And this is annoying because when you click the deploy button, particularly if you're trying to test something that a developer's been working on and you've then got to wait a couple of minutes for it to go out to the staging environment and again a couple of minutes to go out to production, that's just dead time. You're sitting around. And maybe you could go on Reddit, but you probably haven't got enough time to read anything in those. So there's not really any time that you can do. There's nothing you can do in that time. There's also deadlock issues, and this is really irritating when the Puppet run has just happened normally, and you want to press the deploy button, and you've got to wait for the existing Puppet run to complete. Now, in most cases, there are going to be very few changes, but it may be that we've made some change to the Puppet modules at the same time as we want to deploy code, and it takes a couple of minutes to deploy that. This is just annoying, and there's no real way to get around this because you can only have one Puppet agent process running at a time. And it's also eventually consistent. And this means that our deploys go out at different times. They're not completely, they're not synchronized down to the second because the Puppet run takes different amount of time on each server. And as soon as you issue that mcollective run once command, it just tells the Puppet agent, please run at your next possible soonest time. It doesn't say run immediately and block everything else. And this means your deploys are going to go out at different times. Now, in most cases, this doesn't make much difference to us because our code is such that that doesn't matter. But there is one case where it does matter, and that's on the front end. And often the front end changes are very, very granular. So if a customer is hitting one node in the load balancer and then switches to another one because they're randomly distributed based on load, they wouldn't really notice much. But if we're deploying a big feature, then it could be that they hit one node and then they refresh and the code is completely different just because the code hasn't had time to be deployed yet. Now, the way we could do that is because Nginx is within Puppet, and it's defining those variables, is we could just script a process to remove those nodes individually. And so we remove one, deploy, put it back in, remove the next one, deploy, put it back in, and so on. But that's not something that we do currently. It's just the next step that would help us solve that eventually consistent problem. But the biggest problem that we have is that the Puppet agent is slow and it's inconsistent across nodes depending on the spec of those. And we don't really have a solution to that currently. Now, the final use case is how we do system updates, and this is very crude at the moment, but we're working on how we can improve this. But there are a couple of principles that are worth mentioning. Now, at the moment, it's just a simple bash script that runs through every single one of our nodes and gives us prompts to do specific actions. And we're using mcollective to issue the remote commands across the selected nodes. Now, this is the part of the script. At the top, we've got a number of our nodes in our environment defined. And then we've got functions that get executed. And we have a concept called canaries, where we define a representative sample of our entire infrastructure. So in that top list, we have one web server, we have a database server, we have an application server, there's an Nginx server, but it's not every single one of them. It's just one from each cluster. And we deploy system updates to that group of servers, which is representative of the entire environment, and then we stop and we wait and we monitor things so that one server in the group has received the updates, and we can make sure that nothing is broken and that everything remains the same. Our system continues to respond at the same level of performance. There's no regressions, nothing unusual is happening. And of course, we will have tested these updates on staging first and also locally in Vagrant, but doing this on production makes sense because Puppet is the easiest way to very quickly destroy your entire infrastructure. So we do this by specifying the groups, these canaries, so that we can just destroy a small number of servers and not ruin our entire production environment. And once we're happy with this, we then deploy across the entire fleet of servers. We also pay Canonical for support, mainly because we want access to their landscape tool. And this gives us notifications across every single one of our servers so we can see when there are updates to packages available. Now, Canonical publish a security feed, which is very good via RSS, and we schedule in security updates as soon as possible. But for system packages, there's no real source for that. We have to subscribe to mailing lists, and we have to subscribe to security groups, and the libraries that you're using all have different sources. So where possible for our system updates, we get email notifications from Landscape. And this helps us to decide when we want to deploy security updates and when we want to deploy the minor package or the major package updates. And the canary concept really helps us there because it means we can maintain reliability and performance, but still stay up to date on the very latest versions of packages, which is very important for security, but it's also important for the version updates because you don't want to be deployed on old versions of libraries like PHP or Python when your engineers want to use the latest versions of things with the new features. And we also do pinning, and we only do this in a very small number of cases, and this is where we define specific versions of system packages. Now, the only real case that we have for this generally is our database. We want to make sure we're always deploying the same version of the database across every single server. This is so that we don't get automatic updates, but mainly it's because when we're deploying new servers, we want to make sure they're not getting the latest version of the database that's completely different from the rest of the cluster. And although you can generally update in place system packages, and it's generally everything's OK, with the database, you want to do this in a controlled fashion. And in most cases, once you've got large clusters, you have to do it in a specific order. So with MongoDB, you have to update their 3 different components in a specific order when you're using sharding. And so we do this manually to make sure that everything is going OK. But Puppet allows us to pin versions, allows you to specify the version of a package that you want to deploy. And this simply integrates with the system package manager, which is apt on Ubuntu, and just specifies the version that gets deployed. The other use case for doing this is where we have a bug in a version of something. So in one case, we had a bug in the PHP driver for MongoDB, and we used Puppet to deploy that, and we just specified the version so that it wasn't upgrading until we got that fixed down. Now, until 2 weeks ago, this was our environment for the setup that I just described. It was actually slightly more expensive. That was about $503 a month for these 6 VMs that make up our Puppet Master, staging environment, and the builds. And these are all deployed on SoftLayer on their public cloud. But as of last week, we switched over to co-location. We're starting an experiment internally to move away from SoftLayer as a hosting provider, not because we have any problems with them, and they are an excellent provider. We've never had any issues and would highly recommend them. It's just that it's very expensive. And we're replacing those 6 VMs with a single Dell 1U server, which has 2 CPUs, 16 cores, and 32 gig of RAM. And we understand that this is replacing 6 VMs with a single server, so there's now a single point of failure. And also because it's a physical server, if something breaks, we can't just load up new VMs. So we've decided initially we're going to have redundancy on that one server itself. And that's done by mitigating against the components that are most likely to fail. Now, I've never seen CPU and memory to fail in the last 4 years, and you can't really have redundancy on that level. If that happens, then we have to actually go to the data center. But the most likely components to fail are the power supply. So we have dual PSUs, which are hot swappable, the network interface, which is also dual, and hard drives, which are the most likely to fail. And Google has some very good research from 2009 on this, but Backblaze released a really good blog post about 2 weeks ago about the usual time for failures of disks. And you'll usually find that disks will fail either within the first 3 months or after 3 years. And the way we mitigate against this is by having hot swappable drives in a RAID 10 setup so that we can lose 2 drives and still continue working. And we have a single drive that's sitting in the data center so that our hosting provider can just swap it out in the unlikely event that just one of those disks fails. But the next step from that is to deploy another server in a different data center. And we still have that backup slave, the backup hot failover of the Puppet Master in SoftLayer. One of the reasons that we are with SoftLayer is because they have all this hardware in stock, and you pay for it on a monthly basis, and that's pretty much what you're paying for. But the pricing is really, really high when you compare it to dedicated hardware and buying your own boxes. So for example, our database servers with SoftLayer have SSDs. We have an 800 gig SSD in one of these servers, well, in all the servers, but in just one as an example. This 800 gig SSD costs us $300 a month. Well, to buy that is about £350. So after 2 months, we've already bought 1.5 of these. But we're paying again and again and again every single month. And because database servers tend to sit around for a long period of time, you're going to end up paying a huge amount of money. But part of this is because they're storing spares in stock. They will replace them under a time guarantee, and we don't have to go to the data center to do that. And you get that managed level of support. We actually rarely interact with SoftLayer, except when there's problems on their side. We have to open a level 2 support ticket and try and get through level 1 support. But you get that managed environment if you want it. Rackspace have a reputation for this, so if you want to pay them those huge amounts of money, they'll manage everything for you. And this is great if you're a small company and you don't have time to do this, you don't want to do it, which is a fair point of view to have, or you just don't have the expertise in-house. And in particular, having to deal with networking problems is annoying, because usually the network will work perfectly, but then something will go wrong and absolutely everything is broken and you have no idea what is going on. And this is because the hardware is proprietary. You have to learn specific things from the likes of Cisco or the other vendors, and they charge a lot of money for training. And fixing networking problems can be difficult. So just paying someone to deal with that, to build the high-spec network, to spend all that money up front, to build a very reliable network can be worth it. But once you hit a certain amount of money on the spend, it's even more when you're on the cloud, if you're on Amazon or Rackspace Cloud, simply because those environments, in my opinion, are designed for elastic workloads. They're very good if you need instances for a short period of time. But if you're running long-running database servers, for example, then they become very expensive very, very quickly. And so once you move to dedicated, which is a little cheaper, then the next step along from that, which is what we're experimenting with now, is co-location. And you can get significantly higher spec hardware at a much lower cost. And if you notice, the spec of that Dell server was significantly higher than the VMs that we were running. The VMs had about 6 or 7 cores between them, maybe 5 or 6 gig of RAM, whereas this Dell server we've built for expansion, and we're spending a lot less on it. And that's a lot less over a long period of time. So in the first year, you've got that initial upfront cost, but after that, you're just paying for the colo pricing. But it is an upfront cost. Now, if you're a big company, you've got a lot of revenue, or you've got VC backing, then that's not a problem. But as a startup or a small company, then spending 20 or 30K for hardware up front can be a significant outlay. Particularly because you've got to buy the server, and you've also got to set up your networking infrastructure. And generally, the most expensive part is going to be those high-end routers that you need. And you also need internal skills to do this. You have to be able to know which hardware to pick, and you have to be able to build it and deploy it, which isn't so difficult, but what becomes annoying is when you have to go to the data center in the middle of the night or at the weekends to fix obscure hardware issues, because if you have to go to the data center, it means you can't just fix it by paying a data center tech to swap out a disk. But it is a lot more fun, and you get to pick your own hardware and put stickers on it and see a cool server and all the lights and stuff like that. But it can be a little more complicated when you're figuring out the pricing. When you pay SoftLayer, you just pay a monthly fee and that's it. You know exactly what it is. When you pay Amazon, it's an hourly fee and you know what it is. It's a little more difficult when you try and figure out how many IOPS you're doing, but generally the pricing is fairly transparent and straightforward. When you're paying for co-location, at least in London, the pricing is not based on the space in the rack, but is based on power and networking. And power is very difficult to calculate because you can't just take the wattage of the power supply. You have to look at how the data center is billing, and sometimes that's in kilowatt hours, sometimes it's in amps, sometimes there's a minimum commit, there's a maximum commit. In the UK, you have to pay a carbon offset charge, you have to pay a capacity reservation fee, a usage fee. It can be 95th percentile. It's very, very difficult. And this slide is from Telecity, who are one of the providers in London, I think in Europe as well, who we didn't choose. Eventually, we decided to go with Equinix. But you can see from the diagram all these different setup costs and how they bill from it. There's a nice illustration in the picture to try and distract you, but it's actually quite complicated. And the only way to actually figure it out is to buy your server, buy your hardware, plug it into a power meter, and to actually see what it's drawing when you're running your application on it. Because you can max out the CPUs, as we did in our stress testing, and we were using 1.2 amps. But in normal usage, we're using about 0.6. And you want to make sure you've got the right capacity reserved at the data center to handle that. And then networking is on top of that, and you pay usually for a minimum commit based on the megabits per second you're doing, and this decreases in per megabit per second per month pricing as you increase throughput, but it also becomes very expensive very quickly, and you're not based on your actual usage per gigabyte fees that Amazon and the likes charge. And there's also Metro Connect within a city if you need multiple data centers, which you should have, or if you're connecting across regions, across Europe, or it gets even more expensive once you're going around the world. So this is an experiment that we're trying at the moment. We've just deployed our staging environment, our Puppet Master to this. We've improved build times by about 4 times, and Puppet is no longer dying all the time because it's fairly resource intensive. And we're going to see how this goes, and looking to deploy our entire infrastructure from SoftLayer onto our own hardware in 2 data centers in London. And if you go to the blog at blog.serverdensity.com, then I've written up a lot of this. The blog's 99% dev content. Every month we say what we've released in the product, but it's mostly us writing about the technical challenges that we've had, how we fix things, and the Colo project if you're interested, all the pricing, all the hardware details are in.